want to get to that point, can't I go here? Wouldn't that be x comma 3 then? Isn't that what that is? So that's all they're saying here. I can go along x comma 3. I can go ahead and make y get there. Let y get there. Now take it, let x get there slowly. Right? That's how I can get to that point. Another way I can get to that point, the way that people normally think of getting that point would be maybe 1, 1, 2, 2, 3, 3, and then let 3 go to 4. I mean, that's more of a angle direction to get to that point, right? Desperately want you guys to get this. Yes. Feel free. Yeah.
So if x goes to b, it could be f of.
So if I know the limit of this exists, here's the thing I can get from this. If I know the limit of this exists, much like in 2 dimensions, if I know a limit exists at some point, what must that mean? The limit from this direction matches the limit from this direction. And I don't know what it does there, but that's all I need for the limit to exist, right? Now extend that to 3 dimensions. Not just the limit from the left and the right, but the limit from all directions in all different configurations must match. Same thing, it's the same idea. Every single way you can get there. Well, in 2 dimensions, there's 1, 2 ways to get there. Not very exciting. In 3 dimensions, there's an infinite number of ways to get there. If the limit exists, that means every single one of those ways must agree. They must come out to the same number, no matter how I start plugging things in, right? So maybe it would be good to, like back in the day, if I wanted to go towards 2, we would make these crazy little 1.9. Remember these? 1.99, 1.999. Then you go 2.001, 2.01. And so you can see the pattern as you go through, right? You guys remember doing that?
Yeah.
I can do the same damn thing here. Except now I want, so for example, if I want to go to 4, 3, so I can make it a little table like that now, right? How could you go to 4, 3? Well, I could go 4.1, 3.1, 4.01, 3.01. Isn't that one way to do it? Right? Would that get you to 4, 3 if you kept going along that pattern I've set up? How else could you go to 4, 3? I mean, you can't stop thinking of a way to get to 4, 3. There's a lot of different ways to get to 4, 3. You can go, so like the one we're talking about with this problem is I can go there like this, 4.13, 4.013, 4.0013. I can just set y to 3 already, let x kind of come at it, right? That's really what this guy's saying, the x comma b. Let y be there, and let the x come at it. Or you can let x be there, and let the y come at it. Or, here's something that's kind of cool. Couldn't you approach the point 4, 3 along the line y equal x plus, minus 1, obviously, right? Where to get that from? Y equal x minus 1. Why would that line be a path that would work? Because that 4, y would then be 3, right? So I can approach it from there. I can approach it, then if x is 5, what's y? 4, right? And even starting, let's start a little further. If x is 6, y is 5. If x is 5, y is 4. If x is 4.5, y is 3.5. Isn't that going to get you there? Yes, any path that ends or includes that point, 4, 3, that's an acceptable path to use. Right? So I could go along it, y equal x squared minus 13, right? Because at 4, what would that be?
16 minus 13.
Is 3. So it includes this point here, doesn't it? So I can make a table of values for that. Do you guys kind of see how this starts to, you can approach that point in an infinite number of ways. Whereas if I want to approach 3 on the x-axis in 2 dimensions, how many ways is there to do that? I mean, if I want to approach the point x equals 3, I can do it from the negative side, or I can do it from the positive, and that's it. I mean, there's no other way to come at it. There's no other kind of, the minute I add in one more dimension, now I can come at it like this, like this, like this, like this, from the front, from underneath, I can do all this weird shit, right? I can come at it from all these different directions, so it added another dimension to the whole thing. Okay. So again, the homework is not going to be as evil as you think it could be, as it actually could be. Look real quick at the homework. Page 808. So you're going to have the little concept questions at the top. So guys, you're going to have the limits of functions that are just straightforward, just plug and chug. They have no problems. That's number 11 through 24, actually. Then you're going to have the one that tells you right at the title of the problems, non-existence of limits. To prove that limit does not exist, what do you have to do?
Try several paths.
Try a couple paths try several paths until you get two that don't match. So what kind of paths can you take? Anything. But I've given you kind of a couple of ideas. Pick a path that will simplify the expression you're given. Right? For example, let's look at that first one. X plus 2y over x minus 2y? Yeah, cool. Now this is one where my approach would work beautifully, right? Because my approach does sometimes work, thankfully. It's just, well, you always try first, and if they're already different. So what was my approach again? What's one path I could take? Yeah, I could take like y equals 0. So that would make this become the limit as x goes to 0. Yeah, of x over x, which is 1. And what about x equals 0? That would make this become the limit as y goes to 0 of 2y over negative 2y, which is negative 1. There's two paths that don't match. Bam. Right? And if those both came out to the same thing, what other path could you try? The minute that a constant doesn't work, you take a step up. You use a linear. If you can't come up with linear ones that don't work, that make you freak out, then try quadratic. You take steps up in complexity. Most linear ones should get you there, actually. Right? Especially when the problem itself is linear. This is all linear up here. So if I took y equals x, what would that become? Yeah, if I let, it would be 3x over negative 3x. And that's negative 1. So this and this together would tell me that the limit does not exist. Right? Well, y equals x. X minus, that'd be, I got to pay more attention. That'd be negative 3, right? Cool. Why wouldn't I choose y equals x squared here? What's very obvious here why I would not want to do that? Because then you wouldn't have like terms at the end, right? You want something that you can put together and cancel coefficients. That's what you want to have happen. Cool. So if this problem would have been this, what path could you choose? Obviously, the 0, 0 thing still works, but let's say I say you can't do that. I'm being really evil. You can't do what I said you can do. Yeah, you want to make x equal to y squared. You want to go along that path, right? It doesn't have to be y equals a function of x. It could be x equals a function of y. Because in this case, I don't care. They're both stupid dummy variables. I can make them relate to each other any way I want to. I want to go along this sideways parabola. Right? So if you let x equal y squared, you do that because now you'll have like terms. You have something that will simplify to a number, easy to look at, right? Let's see, what else we have in this homework? They talk about continuity. And let me see. I think that's about it. That's as far as this goes. There's not too much in the homework in this section. So I want to do a little bit out of 12.4. And I think I'm going to give you the quiz thing to work on at home and bring back next time. We can go over the answers then. this.
We turned it.
Oh, cool. Thank you.
You're reminded.
Hey, the whole section, we're done.
This is coming from the original plan.
Let me ask you a question here. If I ask you to take the derivative of this, what should be either a question that you have, like, is W itself a function of something here, right? Because that would totally change the approach I would take. So if W is a function of X, then that would be product rule type thing here, right? So if I told you W was a constant, then that'd be awesome, right? How would you take the derivative? 2W. Yeah, 2WX, no problem. So, thankfully, we're going to run into the same problem here, because we have functions that have two valid variables in it, right? So I can have a function like that. And if I say take the derivative of this, they're not functions of t. This is not implicit differentiation or something like that. There's got to be some analog to derivatives when I go to higher dimensions. And one thing that might make sense, for example, and this is the same example in the book. If you're hiking along and you've come up to a point, well, let me just show you the picture in the book. Me drawing is not a good idea. So you're hiking and you get to this point here. And somebody asks you, what's the slope where you're standing right now? It really depends on what? The way you're facing, the way you're about to go, right? If I said, if I'm going to go to here, I would say, okay, the slope seems to be negative, whatever, and give an estimate. If I'm going to go this way, it's going to be positive, whatever. This way it looks like it might be flat for a while, right? So maybe it's 0 in that direction. So these derivatives have to somehow be directional, right? We're not quite to the place where they really get directional derivatives. This isn't quite that yet. But I need to be able to do a derivative in a plane, right? So if I take, let me see if they have another picture. Sort of. Oh, yeah, this is perfect. This might be a little too zoomed in. See if they have, oh, yeah, good, perfect. So look here, they're trying to show you, they've sliced it off. So here's the point that I'm interested in. Let's see, and I want to know the slope right at that point. So you can imagine what they're going to do, and we're not going to go through the whole thing because it's exactly the same as it was in 2 dimensions. I want to bring that point in closer and so forth, but the point I want to make is, if I slice it with this plane, then that means I'm going up this curve while I'm staying on that plane. That's the idea, right? And this plane here is parallel to x, right? So that would be kind of like, at this point, what's the derivative with respect to x? Because I'm letting x move, right? What am I keeping the same on this plane? What's staying the same? Beautiful, right? Y is being kept as a constant then. And then I'm allowing x to change. This is exactly what I do in real life. I don't move in all 3 dimensions at once, believe it or not. But if you think of me as a particle, I can really only move at any point in 2 dimensions, truly. If you really think about it. The minute I move a little bit, isn't that a plane? Doesn't that thing live on a plane? So I can look at this two variables at a time. I can hold the other variable constant. That's exactly what's happening here. As I look on this plane, I'm going to move in some direction and let y be a constant in my equation. Of course, you can do the same thing if you want to know, well, what if I'm going to head the other way? What if I'm going to head and leave x alone? Make x a constant, and I want to move the other direction. Okay, that's going to be a different derivative based on that direction. So these things, well, there's the name of them, and it should kind of make sense. these things we're working with now are called partial derivatives. And you have to tell people. Now, I want to differentiate these things from the derivatives we've done before, which were more like total derivatives. So before I would have had something like this, df dx. Now the partial will be that. It's still basically a d, just a little more cursive, right? In a way, a little more curvy. So that's the symbol for partial derivative. Okay, it could be weird J, I like it. So you can see here in the book, I don't think they should, oh here, at the bottom. This is the way they do it in the book. Right. This I use myself. The book uses this here.
What's alpha look like? Yeah.
Alpha's a little fish. Alpha's a little fish. That's basically what I'm doing.
This is a retarded bee.
I just want you to realize mine are not going to connect in the middle. I just do it too quickly for that, so that's the way mine is going to look. Theirs actually has a little, they connect. That's really the only difference there, right? They actually connect. Those of you who it almost looks like a musical note.
It's a quarter.
Man, mine looks like a two.
So what do you think this is then? In fact, I can be a little more, guys, I can be a little more precise here. And this is not going to be very difficult if you remember derivatives. And I think we all remember our derivatives. It's going to be actually pretty damn simple for the basic ideas of partial derivatives. What would dz, partial of z with respect to x, what would that be? 2x, because what do you do with y when you have a partial with respect to x? You treat y as if it was a constant. And derivative constant is 0. And the partial of z with respect to y would be 2y. Cool. Right? Those of you, I don't think, has anybody taken differential equations? Right. This should be very familiar, especially with like exact differential equations, when you had to prove that the two partials were the same. So you guys have a little bit of a head start on this partial idea. Oh, before I get too far, a quicker way to say this, instead of writing these weird d's, is to say that this would be fx. This is my f of xy. Fy. Yeah. Leave this notation is always sucky. We know that. We have prime notation. Well, this is sort of related to that. But at the heart of it, there's always this leave this notation. So what about this here? You guys figure out what's fx and what's fy. And let's see if you know how to figure out that. When you do this, you treat y as if it's a constant. So it just comes for the ride, unless it's by itself, in which case it goes away. Right? It's like any constant. Of course, this is the right way.
Yeah, I don't even know. I was just like, oh.
I
Yeah. I don't know.
Just equivalent. You mean the derivative of both x and y, or it's just derivative of x multiplied?
This is a subscript, right? So the little x on this means take the partial with respect to x, and then you take partial of that with respect to y. Like a second order derivative, like a second derivative. Right?
Oh, I see.
So the little subscript, obviously, you guys should realize that symbolizes what I'm taking the partial with respect to. So that third one says, take what you got here and then take the partial of what you got here with respect to y. Do it again. Treat it like it's a whole new function of its own. So what do you guys get for f with respect to x? Yeah, 8xy. Cosine xy times y. So you can just put a y up there. Let's put a y up there. Right, that's the y from the chain rule. Right? Sweet. Okay. Some of you guys are coming to life. Feel like, thank God, derivatives. I remember and can do that. Partials should be easy. It actually really should be. F of y would be what? 4 squared.
Minus 2x.
Yeah, 2x cosine xy. Get in there. Now this one says take what you got here and treat it as if that's the function you're starting with, and then just do the partial of y.
8y minus 2x.
Yeah, so treat, what are you treating as if it's a constant now?
No. What if you do okay, see that, right?
Exactly. You're treating, if you're taking it respect to y, you're treating x as if it's a constant. Yeah. 8x plus
2x.
2 cosine x y. I love it. So take the derivative of this, leave that guy alone.
Wait, Fine.
Oh, sorry. Minus. So what has to happen here?
Product
We're taking respect to y. This is a product rule. You got a function of y there, and you got a function of y there.
Damn it.
So if I do the derivative of y first, it's minus 2 times cosine xy. If you do the derivative of the cosine of xy now, that's where it becomes plus, because it's going to be, the derivative of cosine is negative sign. So plus 2, good, xy, sine xy. So again, let's look at that one again. So the first part of it was easy. It's a product rule. Derivative of y is equal to y is 1. Awesome. So there it is. Then you want to leave 2y alone and take the derivative of cosine of xy. We're treating x as if it's a constant. So the derivative of cosine is negative sign. That's why I became a plus. Derivative of xy then would be just x, because we're treating x as if it's a
Why
constant.
do you have that? Why?
Because the y is here. Yeah. So again, this is really exactly just your derivative rule. Nothing new there, really. Oh, here, guys. Let me give you this here. Bring this to you next time. I'll have the